So moving along, now we finally arrive at what we call the photolysis rate constant. And what that photolysis rate constant gives us is the rate constant for chemistry, for a chemical process. So in other words, A absorbs some photons and goes on to make whatever the stable products are. Okay, so we know A is going to absorb a photon and make an excited state. And there's all kinds of possibilities that that excited state can do, including going on to form a product. Okay, and for that specific process, we call that Kp for photolysis rate constant. And as it turns out, this is more often than not the rate determining step. Okay, so all of these other decay mechanisms for excited states are very fast. They're incredibly fast compared to chemistry. All right, so that's why we often only really think about the photolysis rate constant, Kp. We don't worry about the fluorescence rate constant or the internal conversion rate constant or the absorption rate constant because, again, they're very fast. So here's how we calculate a photolysis rate constant. Okay, so it has to be calculated. You can't just have a general photolysis rate constant because it's dependent on the available light. Okay, so dependent on available light. So there's two versions of this equation, so I'll describe them both. So this first one assumes that you have a broad continuous spectrum. Okay, so for example, suppose, so I'm going to say, I'll call this I0 versus lambda. And maybe it looks something like this. And by I0, what I mean is that is my incident radiation to my sample. Okay? So this spectrum that I just kind of drew up here, that would be the spectrum of my light source. Not the spectrum of my molecules, it's the spectrum of my light source. Like what color light am I using? How much intensity there is? And so now you can calculate a photolysis rate constant of that by integrating the quantum yield of absorption of the molecule, right? So, or excuse me, quantum yield for photochemistry. So that's what that gives you. So for the photochemistry, so in other words, phi of photochemistry, let's write it over here, phi of lambda of photochemistry is going to be Kp divided by Kf divided by Kisc divided by Kic divided by Kpf. Okay? And to a reasonable assumption, most photolysis rate constants can assume to be 1. So in other words, when you add up all of these rates, they're all approaching that of the rate of photolysis itself because you're adding up all of those individual processes. Another way to think of it, instead of thinking of it in terms of the rates, really a better way to think of it is if I blast this molecule with 100 photons, all of those contribute to photochemistry. That's more of a reasonable approximation. So now this sigma, you know this, that's the cross section. Okay. Right, and that's in square centimeter per molecule. Quantum yield is unitless. F, this is called the flux. And that's going to have units of photons per square centimeter per second. So you can think of it as the density of light used. So it's very much related to the intensity of light. However, it's flux given that it's photons per square centimeter per second. And then, of course, d lambda, so we would integrate across a broad source of light. Okay? So you can also use this version of the equation. So instead of integrating, you can just do a sum of the products of all three of those things, right? So if you know the quantum yield at a given wavelength, if you know the cross-section at a given wavelength, and you know the flux at a given wavelength, then you just multiply all three of those together, okay? And if you have a monochromatic source of light, so suppose you only have like one single wavelength coming through, then you don't have to carry out that sum, okay? You just multiply them all together and you go for it.